It's a pleasure to introduce Gijs Heuts, who will tell us about Lie algebras and VN periodic spaces.
All right, thank you. And let me thank the organizers for putting together this wonderful event and for inviting me to speak. Hope it will still be wonderful after this hour. Is it on? Is it not on? Is it on now?
No.
Yeah? No, it's not?
Yes. It is. It's on.
Oh, okay. All right. Good. Let's get started. Okay, so the goal here of this talk is to, take rational homotopy theory in Quillen's style and generalize it. And generalize Quillen's rational homotopy theory, but to, other localizations of homotopy theory. So to the telescopic or the monochromatic localizations. Of S star, where this notation for me will always be the homotopy theory of pointed spaces. So this is the homotopy theory of pointed spaces. And I guess for this talk, homotopy theory will just mean infinity category. Okay. So, yeah. What else? All right. So let me just quickly state Quillen's rational homotopy theory to get the essential form of the result that I'm after on the board. So Quillen, of course, proved the following. If you take the infinity category, it's not quite what Quillen said, but fair enough, of say rational pointed spaces, and you take the simply connected ones. Then, he gave two models for this, right? Two algebraic models for thinking about this homotopy theory. On the one hand, this admits a model through differential graded Lie algebras. So let me use the following notation to prove that this is equivalent to, I'll write it as Lie algebras in chain complexes over Q. And, they should be connected. There's a degree shift, which is the same degree shift that, of course, you see in the white-hat brackets on the homotopy groups of a space. So these are DG Lie algebras over Q. And then the other model is in terms of, commutative co-algebras, co-commutative co-algebras, differential graded over the rational numbers. Right. Co-commutative DG co-algebras over Q, and now there's no degree shifting going on, right? So of course this equivalence is something like passing from a space to its rational chains in some appropriate model for those, and this is maybe a little more mysterious, but whatever it does, the Lie algebra you get has as its homology the rational homotopy groups of your space. So it's some enhancement of that construction. All right. So let me first just state the result and then try to explain it. So the homotopy theory that I want to look at today is something that I'll denote M and F, or script M and F. There are various ways of explaining this notation. Let me make it a little bigger, actually. The M maybe stands for monocular. Perhaps the N stands for the height N. The N and the F have the same role as in the L and F that we've seen before. Anyway, this is going to be the thing that you get from S star. So this is the infinity category obtained from pointed spaces by just formally inverting the maps that induce isomorphisms in Vn periodic homotopy groups. I'll say what that means in more detail later. But okay, so this is the thing you get by inverting the Vn periodic homotopy equivalences, or let me just call them equivalences. All right. So with this notation, the theorem is the following. We call it theorem A, not because there's going to be a theorem B, but just so that I can refer to it. So there is an equivalence of infinity categories between this M and F and the infinity category of Lie algebras in Tn local spectra. Okay. All right. So I should probably say a few things about this. For example, what is Lie algebras in Tn local spectra supposed to mean? Well, the kind of thing I have in mind here is the following. So Lie algebras in spectra, or spectral Lie algebras, or whatever. For me, by definition, these are going to be algebras over Michael Ching's operat of the Goodwillie derivatives of the identity. Okay, so these are algebras for Ching's operat, which is, well, the terms in this operat are the Goodwillie derivatives of the identity function on pointed spaces. Goodwillie derivatives of the identity. And then, well, Michael demonstrated how to put an operat structure on those. And that's the operat I have in mind. You can consider algebras over it in spectra. I'm considering algebras that are, well, happen to be Tm local spectra here. Okay, so let me maybe just state a few facts about this operat in case you're not that familiar with it. Here they are. So the first fact is, well, okay, this operat exists. That's fine. Why would you call these things Lie algebras? Let me give two reasons for doing that. The first is you could take the terms in this operat, take the nth one, and compute just its ordinary homology with integral coefficients. Then this turns out to be exactly, well, the nth term in the usual Lie operat in abelian groups, but perhaps with a little degree shifting going on. So, well, this is a graded abelian group, so I'm going to write something that should make sense in graded abelian groups. I shift it up one, and then I tensor it with z in degree -1 to the n. Okay? Yeah, whatever. It's just a twist by the sign representation. It now lives in homological degree 1 minus n. This doesn't really do much. Okay, so an algebra, say in graded abelian groups. So wait, if X is an algebra for this operat, then that's the same thing as the d-suspension of X just being a graded Lie algebra.
Is the suspension describing Lie or the suspension describing Lie n?
Oh, I'm just taking this thing as a module and shifting it up one homological degree.
Like an n-1 suspension?
No, here I'm shifting it up once and then I'm shifting it down n times.
Oh,
So really it's like 1 minus n.
Oh, I'm sorry.
I just wrote this to make the action of the symmetric group
So
explicit.
It's doing two things. It's both getting action of the symmetric group. And
Yeah.
everything. Gotcha.
Yeah, so this doesn't do anything to the action and this will twist it.
Got it. Okay, great.
But so here I'm just making the point that this really doesn't matter very much. I mean, the categories of algebras over this and the category of algebra over this and the category of algebras over the Lie operat are the same, and the equivalences shift in degree. Okay, John?
Is this operat the dual of a co-operat in
Yeah,
spaces?
that's fact number 2. Yeah.
Oh, okay.
Yeah. Right. So, well, this already tells you that this operat is some kind of spectral version of the Lie operat. Another, I find slightly more convincing reason for calling it that is that this is also how Michael constructed this operat structure in the first place. This gadget, this symmetric sequence, arises from a co-bar construction. It's co-bar of the commutative co-operat. Okay? If those words don't mean much to you, then you can just ignore this fact. So this is, by definition, well, it's the totalization of some co-simplicial object, which you get by writing down like the co-bar resolution of that co-operad. So this is like the unit symmetric sequence with just the sphere spectrum in degree 1 and zeros everywhere else, and then there's com, and then com squared, where this is like the composition product on symmetric sequences, and etc. So sort of algebraically, like Ginzburg and Kapranov, maybe in different words, but they recognized that the Lie operad, or the shift of the Lie operad, was the co-bar construction of com, and you can do the same thing in spectra, and that gives exactly that operad. Okay. So that's what Lie algebras are supposed to mean. I should probably make some further remarks about this theorem. Yeah. The first one is maybe, well, I've stated it for Tn local spectra. Maybe you don't like that very much. You prefer Kn local spectra. There's also a version for that. So there's a version of essentially everything I'll say. So you can replace the right-hand side by Kn local spectra, and then you have to, well, maybe localize the left-hand side a little further. That works too, but somehow this is the thing that comes up more naturally here, so I'll stick with that. And the other remark is a little more substantial, maybe. If you compare this theorem A with Quillen's thing, then half of it is missing. So what about co-algebras? Well, you could take this homotopy theory MNF, and you can also compare it to the infinity category of commutative co-algebras in Tn local spectra. So there's a natural functor that does that for you. So, which is essentially just a variant of the suspension spectrum functor. So there's a functor from MNF to co-commutative co-algebras in Tn local spectra. Let me just call that functor sigma infinity, and maybe decorate it with a little Tn. Well, let me give you some description of this functor. So the composite, like you could go from spaces to MNF, sort of the universal functor that inverts these Vn periodic equivalences, and then continue to here via this guy. That functor you can describe as follows. It's just the thing that takes a space X and sends it to, well, you take X, you take its n+1 connected cover, its suspension spectrum, and then Tn localize it. Now that might seem a little random or not, but it's, well, I mean, this functor, it has a universal property, like it comes from the stabilization of this homotopy theory, so it's somehow a natural thing to consider. The point is, this is all well and good, this functor exists, but it's not an equivalence, okay? So this thing is not an equivalence of homotopy theories, or of infinity categories.
But is it the stabilization of MNF?
Well, co-CAlg is not stable, but spectra Tn is the stabilization of MNF, absolutely, yeah. Okay, so somehow there is something slightly funny going on. You know, in rational homotopy theory, the situation is perfectly symmetric. You have two models, they're both equally good because those are equivalences, and you can pass back and forth between these two by some form of Cazul duality, or whatever you want to call it. Well, that just doesn't really happen here. I mean, there are still two sides. You have this Lie algebra side and you have this side. And there are functors, but there's a bias towards the Lie side. Like you get an equivalence there, and here you do not. Okay.
So Gijs?
Yeah.
So by identifying this explicit connective cover, you're using the Tn of certain ideal plane spaces vanishes?
Yeah, I'm using Tomer's result. Yeah. I mean, otherwise you'd have to, if you don't take that result, you have to write dn here, where dn is some rather not very explicit integer, but well, it's like the, yeah, well, you know what it is, I think. But let me write n+1 because apparently that works as well. It's whatever, yeah, well, let me make that point again. It's what the integer you have to put here, it has to be exactly large enough so that the Eilenberg-MacLane spaces below it are Tn acyclic. Like you don't want to see those because those are Vn periodically trivial, so they disappear in MNF. Okay. Right, I want to make one comment about this. So the failure here, it boils down to the fact that if you look at the Goodwillie tower of the identity, then it doesn't always converge in periodic homotopy. So this boils down to the problems with the convergence of the Goodwillie tower in periodic homotopy groups. Okay, I'm just going to leave that as a slightly cryptic comment. The thing is, sometimes it does work. Like on spheres, you're okay. So this thing, so it is fully faithful when you're only looking at spheres. And if you wanted to prove this, this depends on a result of Aron and Mahold. We'll prove that the Goodwillie tower converges on spheres in periodic homotopy. But it's, for example, it's not fully faithful on more spaces. So that's something I did at some point with Lucas Brantner. Okay. So whatever this coalgebra model is, it's not perfect. It's still very useful, though. Maybe, well, one complaint you could raise is that, well, I said this functor is not an equivalence. Maybe I just wrote down a silly functor. But you can prove that sort of abstractly these two infinity categories cannot be equivalent. They just have different formal properties. Okay? So there can never be an equivalence between those. All right. So that's it for the statement of the theorem and comments on it. So let me sort of take a step back and explain this MNF in more detail. Let me talk a little bit about telescopic unstable homotopy theory. Any questions, by the way, about this stuff, John?
What if you take, you start out having taken some sort of connectivity assumptions on your spaces?
Yeah, so the thing is, in MNF you sort of can't, because, I mean, this is about periodic homotopy groups, and periodic homotopy groups don't care about taking highly connected covers, because it's all over the place.
Yeah.
So that will never, the issue has nothing to do with connectivity. I mean, this functor from spaces to MNF, you can factor it through k connected spaces for arbitrarily high k. Doesn't matter. Okay. All right. Other questions? So let me first say something stupid. Let me define the rational homotopy groups. So the rational homotopy groups of a space, well, how do those arise? Well, you look at homotopy groups, and then you invert P. I'm working P locally everywhere. I should have said that a little earlier, maybe, but that was implicit, okay? Everything is P local. All right. So, okay, you start with pointed homotopy classes of maps from spheres to a space X, and then you invert the action of the self map of degree P on the sphere. So, of course, in similar vein, you can define the Vn, or let's start with the V1 periodic homotopy groups of any space, maybe with coefficients. So let me define the V1 periodic, maybe mod P homotopy groups So what you do, you start by looking at maps not from a sphere but from a Moore space, sk mod p into x. Those are the mod p homotopy groups of your space, and now you invert the action of the Adams map. So that's the map that's often called alpha, that goes from some suspension of the Moore space to itself. All right, so sigma d of sk mod p to sk mod p. So d in this case would be 2 times p minus 1 if p is odd, and it would be 8 if p was 2. Anyway. All right, so that gives something that's sort of deserves to be called V1 periodic homotopy groups. And of course, you could play the same game with any Vn self-map of a space. So more generally, if I had a finite pointed space, if V is a finite, that means finitely many cells, of course, finite pointed space, let's say of type n, meaning its suspension spectrum is a spectrum of type n with a Vn self-map. Let's call it little v. So that's a map from some suspension of v to v. Then I can define the V periodic homotopy groups of a space X. In exactly the same style, right? You look at homotopy classes of maps from V into X, or suspensions of V into X, and you invert the action of little v, right? So you invert the action of little v on the homotopy groups of the space of pointed maps from V to X. Okay, so let me give a slightly better definition, or at least a slightly more useful one. These homotopy groups, these V-periodic homotopy groups, are actually the homotopy groups of a spectrum. Okay, let me define that spectrum. So let me define what's called the telescopic functor associated to V. So that's a functor that is usually denoted capital Phi sub V, and it goes from pointed spaces to spectra. And let me just define it by explicitly describing the values of this functor. So I'm just going to describe the constituent spaces of the spectrum phi v of x. So the zeroth space, by definition, is the space of pointed maps from v to x, and the dth space is the same thing. And in fact, I want to do this for every multiple of d. So phi vx of k d is always that. And then I have to give you some structure maps to make this a spectrum. And hopefully you can see where this is going. Okay. So the structure maps, these should go from phi vx k d to, well, I only specified these spaces for multiples of d, so I can go into the next one, and then I have to put loops d over here. This is by definition pointed maps from v to x, and this is equivalent to pointed maps. I'm just going to take the loops d in at the cost of turning it into a suspension into there, and now there's an obvious connecting map, and it's precomposition by little v. Right. So that's the functor from spaces to spectra, and you'll observe that the homotopy groups of this spectrum, these are precisely the V periodic homotopy groups of X. Okay. All right.
And this is independent of big V?
No, it's not.
Oh,
That was my next point. So
sorry.
you're very helpful. All right. So as John points out, this definition depends on choices. Actually, it only depends on the choice of capital V. I mean, the notation suggests little v, but the sort of asymptotic uniqueness of these self maps tells you that that choice doesn't really matter. Okay, so let me say it like this. These various telescopic functors, the various phi sub v, they can be packaged into one functor. And that one deserves a special name. That's the Gauss-Kuhn functor. All right, that's the functor that's just called phi. And it goes from spaces to spectra, but actually it will land in the subcategory of Tn local spectra. So let me write it like that. So let me just give you the essential properties of this functor. And I mean, the idea roughly is you kind of take all of these and then take the homotopy limit over all finite type n spaces V. Now that statement doesn't really make sense, but you can fix it. The properties of this functor, first of all, well, you can retrieve the phi sub v's from it, phi sub v's. So if you, well, phi sub v is equivalent to dv, so this is the Spaniel-Whitehead dual of capital V, smash phi. All right? Or I could write the function spectrum from capital V into phi. So as soon as you introduce V coefficients, so to say, you retrieve these functors. And this is, in the appropriate sense, this equivalence is natural in capital V. And the other property, which is sort of the reason that this functor came to be, is you could take phi and you could precompose it with loops infinity. So loops infinity is a functor from spectra to pointed spaces, and then you go from pointed spaces to Tn local spectra. There's only one obvious functor other than 0 that does that, and that's the one, okay? So this is Tn localization. So this is sort of the crucial property of the Gauss-Kuhn functor. It tells you that a Tn local spectrum really only, well, it's completely determined by its 0th space without caring about the infinite loop space structure. So it's a very strong, unique de-looping result. Yeah. This is also sort of the existence of this functor is the crucial point that, well, sets this whole Vn periodic homotopy theory apart from ordinary integral homotopy theory. Like integrally, there's never any chance of a functor like this existing, of course, because there's no such thing as unique de-looping in general. Okay, maybe another remark here is that actually phi is determined up to equivalence. It's essentially determined already by property 1 alone. I mean, the way you actually build it is you write down a resolution of the Tn local sphere by finite type n complexes. So you write down just a directed system whose colimit is Tn equivalent to the sphere, and you take the homotopy limit of the associated telescopic functors. That's phi. Okay. Now let me give you a definition. So I'll call a map a Vn periodic equivalence precisely if it's an equivalence after you apply phi. Okay. So a map F for pointed spaces is a Vn periodic equivalence if phi f is an equivalence. And actually, just as an aside, this is equivalent to saying that phi sub v f is an equivalence for any choice of capital V, little v. So in practice, you only have to check it for one of these. It follows essentially from the thick subcategory theorem. Okay, so I could have given this definition earlier, but using capital phi also makes it clearer that it's independent of choices, maybe. All right, so rational homotopy theory is something you build by, you start with pointed spaces and then you universally invert the rational equivalences. So you want to do the same thing here. You want to take S star and invert these Vn periodic equivalences. And the question, of course, is, well, is that even possible? And the answer is yes. And of course, Bousfield is your man. So here's a theorem consisting of two parts. So the first part basically extract this from work of Bousfield and Dror-Forjun. They both did a lot of work on sort of the localizations in unstable homotopy theory. So let me state it like this: the localization of S star at the Vn periodic equivalences exists. Let me be a little more precise. Let me just state the universal property of MNF for you. So there exists a functor. I'm going to call it just capital M from S star to script MNF, which has the following, well, it should be the universal thing that inverts these Vn equivalences, right? So, such that for any test infinity category C, the following is an equivalence. All right, so you could look at functors from M and F into C, and you could precompose by capital M, and you would land in functors from spaces to C. Now this is not an equivalence, but it will be fully faithful, and its image is the full subcategory of functors that send Vn periodic equivalences to equivalences. So it's the full subcategory of functors sending these Vn equivalences to equivalences in C. Right? That's just what it means to universally invert these things. One thing to stress about this theorem is, despite the name Bousfield appearing, this is not an example of left Bousfield localization. Okay? So this functor is not a left adjoint. So it does universally invert the equivalences, but not in a colimit preserving way or whatever. All right. The second part of this theorem, let me attribute that just to Bousfield, is that, well, I mean, by this theorem, I can reinterpret the Bousfield-Kuhn functor as going not from spaces to spectra, but from this MNF to spectra. Because by definition, it preserves, well, it sends Vn equivalences to equivalences, so it factors over a functor from MNF to Tn local spectra. I'll just abuse notation by not changing it. And this now has a left adjoint. Called theta. Right. So it's not true before localizing. If you think of phi just as a functor from S star to Tn local spectra, then it doesn't have an adjoint. It doesn't even preserve all limits. It only preserves finite limits. But if you do this, then suddenly it does.
How does theta relate to Luke's infinity of the underlying spectrum? Or like?
I mean,
because it's like the
I mean, there's a natural transformation from theta to loops infinity, and that is very far from being an equivalence. It's if you want to make the comparison with algebras over an operette, then theta will behave like the free algebra functor, and loops infinity will behave like the trivial algebra functor. Okay. All right. Yeah. Well, I can talk about the construction of MNF, but let me maybe move on. We can talk about that later. So the diagram I like to draw at this point is, well, we now have two adjunctions here that relate this homotopy theory MNF to something stable, namely Tn local spectra. So there's MNF, and there's this adjunction between theta and phi that I just described. So I'll put my left adjoints on top. There's theta phi over here, and there's also sort of the thing you'd expect to be there, which is stabilization. So there's also sigma infinity Tn, loops infinity Tn into here. So this is really the stabilization of this infinity category. So you have, well, the adjunction on the right is sort of what you always have, also integrally without localizing, and this is sort of the special thing that you only have in the Vn periodic setting. And these two adjunctions have the property that they cancel out. If you compose them, I'm just sort of reiterating that property 2 of the Bouwschild-Koen functor, more or less. This is the identity of Tn local spectra, and of course this is also true if you pass to the left adjoints. So same thing is true for these. So one thing that's already funny about this is that this shows that every spectrum is Tn locally a suspension spectrum. This is more or less how Bouwschild did. Well, this is exactly how we observed that. Anyway. So it turns out that's kind of a special thing to happen, and most of what will come after sort of leverages this fact. Maybe there's one comment that I want to make. It's sort of a loose end, but let me phrase it as a question. Sort of besides the point, but let me phrase it anyway. So this is characterized by some universal property, namely that stabilization. This here is just, well, it's something that you construct, right? You construct phi and then you prove it has a left adjoint. Well, the natural guess, if you look at this picture, is that this is the co-stabilization, okay? So is phi the co-stabilization, whatever that means? Well, you can say what it means, but is this the co-stabilization of MNF? All right, so this is a question that I spent some time thinking about with in a joint project with Leonard Meyer and Akil Matthew and Rosona Eldred, and at some point we thought we had a proof for this, and we've sort of fallen from that belief. So we don't have a proof for this, but it would be nice. It's somehow sort of aesthetically would make this picture more symmetric, and more importantly, it would give the Bouwschild-Koen functor a universal property, rather than just constructing it. And universal properties are nice. So, okay. All right. So what do you get from this picture? Well, whenever you have an adjunction, you get a monad. So from this picture, you see that phi theta is a monad on Tn local spectra, and you can factor the Bouwschild-Koen functor. You can factor phi as, well, you start with MNF, and then you go to the category of algebras or modules for this monad, phi theta on Tn local spectra, and then you forget to Tn local spectra. Okay, so nothing happened. This is just category theory. This first arrow, let me just label it little phi. But now I can break the proof of theorem A into two parts. So the proof of theorem A will roughly go as follows. The first part is you prove that this little phi is an equivalence and then the second part is, well, you relate this to Lie algebras somehow. So you prove that algebras for this monad, this is the same thing as these sort of funny Lie algebras in spectra. Okay. All right. All right, so I'll just sketch an outline of these two parts, because at the end I'd like to bring it back to earth a little bit and give some examples or some consequences. So part one, this is joint work with Razona, I mentioned before, and what's the alphabet? Akil, Matthew, and Leonard Meyer. So how do you prove that something like that is an equivalence? Well, you use what's called the Bar-Beck theorem, right? So this is something that allows you to check that the junctions are monadic, and in the infinity category setting, this is now often called the Bar-Beck-Lurie theorem. Well, it suffices to check two things. First of all, you have to check that your functor is conservative and detects equivalences. Well, we sort of more or less rigged that by definition of MNF, so that's fine. That's easy. The other thing is, well, you have to check something about colimits of simplicial objects. If you read the fine print, it's sort of a slightly subtle condition, but you can prove something slightly stronger, which implies it here. Phi actually preserves all delta op shaped colimits. Okay, so this implies the more subtle condition that actually appears in the statement of this theorem. I won't give you the details of this proof, but the key fact is something completely classical. It's the following. So phi is built out of these telescopic functors phi sub v, so you can sort of easily reduce to one of those. And those in turn are built out of functors of the form map star v blank, okay? And now, if you look at a functor like this, so this is just a functor from spaces to spaces. Something like this does not preserve arbitrary geometric realizations, but it does preserve geometric realizations of sufficiently connected diagrams, right? If you, in the special case where v is S1, this is sort of familiar. So then this is the loops functor. So loops will commute with geometric realizations over diagrams of connected spaces. That's a completely classical fact. And you could use that and induction to prove this for any finite complex, okay? So this will preserve delta op shaped colimits of diagrams of spaces that are at least the dimension of V connected. So V is a finite complex, so this is well defined. Okay. All right. That's sort of the only, other than some formal manipulations, the only ingredient you really use. Okay. So that's part one. What about part two? Well, I have to somehow relate phi theta to something having to do with Lie algebras. So, right. So for that I have to, well, go on a short digression about operads or co-operads in TM local spectra. So, it turns out that being in TM local spectra offers you various shortcuts to make your life a lot easier. Like you can shortcut most of this, infinity operads business that I don't want to talk about. Okay, so this is going to be about part 2 of that proof over there. So here's the definition. Let me call a functor f from Tn local spectra to itself co-analytic if it is of the form, well, if it looks like it came from a symmetric sequence, okay? So it should be of the form f of a spectrum E is naturally equivalent to big infinite wedge of something like OK smash e to the k, and then homotopy orbits, and then, well, I should Tn localize the result again. So here OK is some symmetric sequence, okay? Okay, so symmetric sequence just means a sequence of spectra indexed by the positive natural numbers where the kth term has an action of the symmetric group on k letters. Okay, so, well, the terminology is sort of motivated by Goodwillie calculus or dual Goodwillie calculus. Not really very important. Let me call the infinity category of these things. Let me introduce some notation. Let me write co-an Tn local spectra just for the full subcategory of functors from Tn local spectra to itself on these guys. Okay. So the claim is this is actually going to be my replacement for the category of symmetric sequences here. I mean, normally one way to build operads is by saying, well, there are monoids in symmetric sequences for the composition product. And that's what I'm going to mimic over here, but without actually sort of really trying to write down a definition of the composition product, because that's just kind of annoying to do in this infinity categorical setting. And so you don't have to, that's the point. So here's a fact. Well, there's sort of an evident functor that assigns to a symmetric sequence of Tn local spectra such a co-analytic functor. I mean, essentially, you take your symmetric sequence and you write down that formula. If I wasn't in the local setting, then that functor is, I mean, it's not going to be an equivalence. Like, it's not fully faithful. It's not true that, if I forget about Tn localization for a second, that any natural transformation between functors of this form splits into homogeneous pieces. That's just nonsense. But here it does. So this is an equivalence. Okay, so maybe let me just quickly say the ingredients for proving this are essentially, well, you have to use Tate vanishing in the Tn local category, so that's a result of Kuhn. And so that tells you that there can't be sort of any natural transformations between homogeneous functors of different degrees. That's good. But then you still have to do one other thing. If you're mapping a homogeneous functor into something of this form, you have to argue that you can sort of commute the maps past the infinite sum. Like, that's generally not going to fly, but here, again, it will. So this uses a little nilpotence trick that, well, I mean, who comes up with nilpotence tricks? Thank you. So, all right, and ultimately this trick again depends on Tate vanishing, but it's really a little extra argument that I learned from him. Okay, so that's an equivalence that's very useful because this has an obvious composition structure. Okay, so co-an is monoidal just using composition of functors. That's pretty well defined. All right, so that saves me the trouble of defining it over there.
But if you use this to define a monoidal structure on symmetric sequences,
Yeah.
you get something that looks like the composition?
Yeah, it is exactly the composition
Oh,
product. But, yeah, I mean, the definition of the composition product is rigged so that it's sort of compatible with composition of the associated functors. Right? That's why you define it the way you do.
Sure.
All right, so, well, this suggests a definition. Normally you'd say an operad is a monoid in symmetric sequences. So now you just say an operad is a monoid in this thing. All right. I mean, of course, if you wanted to like compare this thing I'm setting up to something more rigid, at some point you're going to have to sort of face it and yeah, compare it to something more rigid. That's not what I'm going to do here. All right, so let me just give you a quick example. And of course, you define a co-operad dually. It's a co-monoid in co-analytic functors. That's fine as a definition, but well, again, you have to be able to give examples. So here's an example of a co-operad. Look at the functor sigma infinity Tn loops infinity Tn. So apply that to a spectrum E. It turns out that this always, well, this is going to look a little bit like Snaith splitting, but it secretly isn't quite. But this will always split. Okay, this always looks like just the symmetric algebra on E. All right. So this, again, this relies on a theorem of Kuhn. So Nick Kuhn analyzed the Tn localization of just sigma infinity loops infinity, and he shows that it splits in certain cases, and those cases are exactly what you need to prove this. Anyway, this functor is co-analytic, so manifestly it's also a comonad. So it's a co-monoid in here, so it's a co-operad, okay? And, well, actually, this thing deserves to be called the commutative co-operad. I mean, this formula is already highly suggestive of that. I mean, the terms are just the Tn local sphere spectrum everywhere. But I mean, you maybe have to make a slightly more elaborate argument to argue that the co-operad structure is really the one that you'd want to see. But that works out. So now the thing, of course, is you want to prove that phi theta, which is a monad, is actually an operad in this sense. And for that, you need a little sort of recognition result. There is a proposition, something that came out of some conversations with Jacob Lurie. A functor f from Tn local spectra to itself is co-analytic. Well, here's another condition. F preserves sifted colimits. So sifted means filtered plus geometric realizations, colimits over delta op. If you preserve those two things, then you preserve sifted colimits. So it's kind of easy to check that this is true. It sort of follows directly from the formula and some basic facts about sifted colimits, but this goes both ways, okay? In fact, this also implies this. So the way that you prove something like this is actually, if you have a functor that preserves sifted colimits, you can kind of resolve it in terms of functors that look like that. And yeah, it's an inductive argument in essence. Anyway, this is very useful because this allows you to recognize co-analytic functors without, yeah. So here's the key example. Maybe I should call it a corollary. If I look at phi theta, I mean, theta is a left adjoint, so this preserves all colimits. Phi, I already said, preserves geometric realizations, preserves colimits over delta op, and checking that it preserves filtered colimits is easy. So it preserves sifted colimits, therefore the composition does, so this is an operad. I mean, this argument shows that it's of this special form. It looks like a co-analytic functor. And then the only remaining question is, well, which one? But sort of at this point, like the serious work is over. If you know that it's an operad, then figuring out which one it is not very hard. So here's the trick, or I don't know, trick is not the right word, but here's what you do. You take the normal, the Bausfield-Kahn resolution of the identity. But you do it for the identity functor of this homotopy theory MNF. So take the identity of MNF, and then you take, well, what's usually called maybe the Q resolution or something like that. Loops infinity Tn. So you get this cosimplicial gadget. Okay, so you can always write this down. And now you just squeeze it in between phi and theta. So I post-compose with phi, pre-compose with theta. And what does that do? Well, it turns the first term into phi theta. And then here, the phi will cancel the loop's infinity. The theta will cancel this one. This is the identity of Tn local spectra. And then here it will cancel the two outer functors. Like so. Okay, so you get a sort of a co-augmented, co-simplicial object like this. So in particular, this gives you a map from phi theta into, well, exactly what I already sort of defined to be the cobar construction of, I'm just going to relabel this thing com. Okay, so that's your map. It goes from one opera to another, and you have to check that it's an equivalence. And that theorem, this thing is an equivalence. And actually, once you've set all this up, proving this theorem is not hard. This is really just a routine. Essentially, you have to calculate the Goodwillie derivatives of both sides. This sort of reproduces the way that Aron and Ching also look at the Goodwillie derivatives of the identity. It's the same style of argument. Okay. That's more or less the conclusion of the outline of the proof of theorem A. That's how that goes. All right. I want to spend my last few minutes just listing a few consequences of this. I mean, what does this kind of theorem actually buy you? Just try to indicate briefly some things. So first of all, this stuff is very closely related to the work of Mark Behrens and Charles Resk on the relation between the Goodwillie tower and the Bausfield-Kuhn functor. So essentially, that's something about passing back and forth between the Lie algebra model and the co-algebra model. So there's a natural transformation, which is called the comparison map. So this is mimicking rational homotopy theory. So it goes from the Lie algebra model, so phi of x, to, well, you could write down the co-algebra associated to a space. And then you could take its, primitives, maybe in the derived sense. So these are the derived primitives. Whatever that means. I mean, it's a construction that's formally dual to the construction of TAQ of a commutative ring spectrum. Okay, so let me call it gamma. So this is more or less also the thing that Behrens and Resk study, although it's Kn instead of Tn, and maybe they're actually working with TAQ of the Spanier-Whitehead dual of this thing. So it's like a double dual version of this. This comparison map is not always an equivalence, basically because of the fact I stated earlier, but it is. So this is an equivalence when X is a sphere, for example. So that's extremely helpful because this side of the story is something that you can potentially compute. Like the definition of phi itself, just from the definition, is hard to compute phi. Okay, so you need some tools, and this is a very useful tool. All right. Okay. Here's another consequence, which sort of drops out pretty easily. You can use this kind of lingo to analyze the value of the Bausfield-Kuhn functor on a generalized Moore space, or like a type n space. So if V is finite type n space with a Vn self-map, little v. Now let me write W for the double suspension of V. I have to do this for some technical reason. Then you get the following formula for phi of W. It's actually breaks up as a big sum of, you put the derivatives of the identity here, and then the suspension spectrum of W here. Okay, so this formula actually corresponds to the fact that if you take this W and you interpret it as a Lie algebra, it happens to be a free Lie algebra. So that's where you get this formula from. So this, this gives you an expression for the value of the Bausch-Kuhn functor on, for example, a Moore space at height 1 in terms of stuff that's completely, and this is completely stable homotopy theory, okay? So it translates the calculation of the V1 periodic homotopy groups of a Moore space, those are known, but okay, completely into stable terms. But it does that for every finite type n space. And then the last thing I want to say is, if you're thinking about Lie algebras, then this suspension spectrum functor is really, from the perspective of Lie algebras, it's the Chevalier-Eilenberg homology functor. If you're thinking about classical Chevalier-Eilenberg homology, that has a natural filtration, sort of by the underlying algebra is sim star, so you can sort of filter sim star by the word length. So the same thing happens here. So this always has a natural filtration with associated graded just the symmetric powers of phi of x. So this is very similar to what happens for Chevalier-Eilenberg homology. And this filtration is weird. Let me just give one example and then I'll stop. So for example, you get a filtration. And if you just take height 1 and you take a sphere, you get a filtration of the K1 local sphere. I mean, not that you'd need help computing its homotopy groups, but whatever. You get a filtration of the K1 local sphere with associated graded. Well, what is phi of an unstable sphere? That's essentially a Moore spectrum. So this will look like S mod p to the L. I mean, you can do this for any L to the K. So you get the extended powers of these Moore spectra, K1 localized, and there's some degree shifting going on. But essentially, you get a filtration of the K1 local sphere with associated graded that looks like this. And you can do something similar for all sorts of spectra that naturally arise as a suspension spectrum. And I don't really understand these filtrations very well. They don't look like anything I recognize. So if anyone has any ideas, I'd be happy to talk about that. All right, let me stop there.
Questions?
Tyler?
So where does this, so you said the associated graded, there's L and K both in there. Where does the L come in?
The L comes from which sphere I chose. Like, I mean, if I want to study the sphere spectrum, I can look at it as a suspension spectrum of any sphere, and the L corresponds to the dimension of the sphere that I picked. Or, well, if I pick S2L plus 1, then phi of it will be essentially the mod p to the L Moore spectrum. Maybe I should have said this is at an odd prime. At p is 2, yeah, it's slightly more fiddly, but okay.
Any further questions? All right, then we'll copy immediately and let's thank Gijs again.